All right, so I handed out a couple of periodic tables for your reference. It has to do with electron configuration, so hopefully I'll lecture about that today. If not, probably we'll do it next week or through a lecture video. So right now we are on Chapter 7, and let me just review some of the key points. Thank you. Let me review some of the key points of Chapter 7. We're talking about light. We're talking about the electrons. Okay. The whole concept here is this idea of wave-particle duality. Okay. Is it a wave? Yes, it has properties of a wave. Is it a particle? Yes, it has properties of a particle. So wave-particle duality. Okay, so that's main point number 1. Okay, light as a particle, I'm going to call it photons. So that's a word you'll see and hear in your textbooks, or you'll encounter in your MCAT or whatever exams you're taking. Photons, that's usually light in the particle form. Okay, so that's main point number 1, wave-particle duality. Main point number 2, we talked a little bit about electromagnetic radiation. Actually, more specifically, we talked about the electromagnetic spectrum. Okay, everything in our lives probably revolves around the electromagnetic spectrum. There's even a portion of the electromagnetic spectrum that we can see. Okay, that's the visible region of the electromagnetic spectrum. So a couple of main points I want you guys to recognize. This would be good multiple choice questions for an exam as we kind of approach the end of the course. One is that these guys travel at the speed of light. Okay, speed of light c. These waves travel at c, which is 3 times 10 to the 8 meters per second. Okay, so the wavelength times frequency, multiply those two together, you'll get c, speed of light. Okay, frequency is in units of hertz, which is 1 over seconds, hertz. Frequency is hertz, 1 over second. Frequency is 1 over second hertz. Frequency is 1 over second hertz. Frequency is 1 over second, and that's hertz. Okay, when these waves travel, they're going to travel at a certain frequency. We call it hertz. All right, so that's one thing about the electromagnetic spectrum. Point 1. Point 2 here is it's actually 2 waves traveling perpendicularly together. So don't get tripped up on any multiple choice portion of the exam. How are you? Okay, it's a E field wave and a magnetic field wave traveling perpendicularly to each other. E field, we call that the magnetic field wave. E field wave and a B field wave, and they're traveling perpendicular to one another. Okay, so electric field wave, I'm going to do an E with an arrow. And magnetic field wave, I'll do a B with an arrow for magnetic field. And the electromagnetic spectrum is E field waves, B field waves traveling perpendicular to one another. Perpendicularly. Okay, that's point number 2. Point number 3 is this idea of quanta. Okay, there's a certain type of energy that is inherent in this electromagnetic spectrum. Obviously, you probably recognize it. All right, there's definitely energy associated. Again, sorry, this is not in color. There's definitely energy related to X-rays and gamma rays. You definitely can feel it. There's energy in this light, in visible light, right? The black mask of Harris, it's actually emitting electromagnetic spectrum radiation, and I could see it. Okay, it's being processed by my eyes. It's not really harmful radiation like an X-ray, but yes, the black mask is giving off radiation my eyes can see. So there's a portion of the spectrum we can see, kind of harmless. There's a portion of the spectrum we can hear, okay, kind of harmless. There's a portion of the spectrum, that, I don't know, sun, UV, IR, okay, all of this is energy. Okay, all of this is energy. Okay, and that energy comes in the form of quanta. Okay, the energy equation is this: E equals H times V. Okay, H times V. Okay, and the energy comes in the form of a quanta, which is like a packet of energy. You think of stadium steps. Okay. And H is Planck's constant. I'll give you that on the exam. V is frequency. Frequency is in hertz. Okay, frequency is in hertz. And finally, our last main point here is this excitation and emission. Okay. So imagine you're an atom, and how many of you play video games? Okay. So my other sections, I asked the same question, and all the guys raised their hands. So in a video game, there's levels, right? Level 1, level 2, level 3. Okay. So we're going to call that level 1 here. This is within the atom. Okay, this is within the atom. So we'll have energy level 1, energy level 2, energy level 3. Okay. On the y-axis here, there's energy. Energy level, 4, 5, 6. You can do this all the way to infinity. And let's just have an electron here. Okay, so here's our atom. And what we're going to do is we're going to hit it with a quanta. Okay, we're going to hit it with a quanta of energy. Okay, when we hit it with a quanta of energy, what happens is that normally from the ground state, okay, call this the ground state, what happens is that, let's say I hit it with enough quanta, different packet, nothing more, nothing less, and it gets excited to, let's say, n equals 3. Okay, we're going to call that excitation. Okay, so going upwards, this is all inside the atom. Okay, we're calling this excitation. Okay, so going up. Okay, so what happens after something gets excited? Okay, what's normally what happens after excitation? What happens after your children get excited and they play around? What will they do afterwards? Okay, they kind of crash, right? Okay, and we're going to call that relaxation. Okay, so it will relax back. So this electron will, okay, we excited it with a quanta to promote it to energy level 3. Again, this is inside the atom to energy level 3. It's going to relax. Okay, like almost anything, like a child, it was going to relax back down. Okay. So we're going to call going down relaxation, but something happens when we do relaxation. It's going to relax back down to ground state. Okay, but something happens when it relaxes back down. Okay, anybody want to guess what happens as it relaxes back down? As it relaxes back down, it emits. Okay, so there's excitation, and then there is emission. Okay, it's going to emit. Okay, so what will it emit? Okay, it will emit energy. That's part of the electromagnetic spectrum. It could emit visible, it could emit UV, it could emit IR. emit anything. In fact, I think we mentioned this at the closing of last week. Okay, we have, let me get this out of the way here. All of these elements you see here are emission spectra. They just so happen to emit in the visible region of the electromagnetic spectrum. Okay, but it can also emit in the UV region. It could emit IR region, any region in the electromagnetic spectrum. But here it's visible. All these lines are things we can see, visible light. So that's what happens as it relaxes back down. As it relaxes back down, it could emit energy. Right? It emits energy. You can see that, at least those that are visible. Okay, that is in this region of the electromagnetic spectrum. Okay, that tiny, tiny, tiny little slither. So, excitation, relaxation, as it relaxes, it emits. All of this is because of you excite it with a quanta. Okay, this whole phenomena is called the photoelectric effect. Okay, photoelectric effect. This is what Albert Einstein discovered. Well, Albert Einstein and others. So. Okay, this idea of excitation. From the ground state you promote, and then as you promote it relaxes back down. As it relaxes back down to ground state, it emits energy. Right. As it emits energy, what do you think the sign will be? Positive or negative? It's emitting. It's going to be negative. Okay, very good. Okay, if you're exciting, you're hitting it with a quanta, what do you think the sign is going to be? Positive or negative? Okay, it's going to be positive because you or whomever is literally exciting it with a quanta. All right, let's do a problem here, and then I'd like to talk about electron configuration and see how far we get into that. All right, so the energy of a photon is 5.87 times 10 to the minus 20. Okay, what is the wavelength in nanometers? Okay, so let's just step back for a moment, step away from the weeds, step away from the dirty math. Not that it's dirty. Just want to tell you guys one thing. So a photon, generally we associate a photon with particle, is it not? Right? A photon is like a particle, light particles. But what is this question asking? Okay, it's asking for a wavelength. Okay, what do we associate a wavelength with? We associate a wavelength with waves, right? Is it not so? Right? So here's something that's particle-like, talking about photons. And it's asking for something that's wavelength, which is something we associate with waves. So again, wave-particle duality. Okay? Wave-particle duality. All right, so how will we solve this type of problem? So we're going to use E equals hv, okay, where h is Planck's constant. And h is Planck's constant. I'll give you this on the exam. So it's 6.63 times 10 to the minus 34 joules times second. And then don't forget frequency is in hertz. These things travel at the speed of light. Okay, wavelength times frequency is equal to c. And c, I'll give you this on the test, is also 3.00 times 10 to the 8 meters per second. All right, so the energy here is 5.87 times 10 to the minus 20. So let's put that in for our E. And And I'm going to divide it by Planck's constant to get V frequency. Planck's constant is 6.63 times 10 to the minus 34 joules over second. Okay, recognize that our joules and joules will cancel, leaving us with 1 over second, which is hertz. 1 over second is hertz. So let's do this on our calculator here. 5.87 exponent on my calculator, that's EXP. Minus 20. Okay, divide this by, let's put our parentheses in, 6.63 exponent minus 34. Let's close those parentheses now. And getting 8.85 times 10 to the 13 hertz. Hertz is 1 over second, hertz. So 8.85 times 10 to the 13 hertz, which is the same thing as 1 over second. All right, so that's our V. So we can plug that in here, and we should be able to solve for wavelength, realizing that wavelength is c over frequency v. And our c is the constant speed of light, which is 3 times 10 to the 8 meters per second. Meters per second. And then our frequency v is 8.85 times 10 to the 13 hertz. Hertz, I'm going to use 1 over second as its definition. Remember, hertz is 1 over second. All right, the seconds canceled, so let's take 3 times 10 to the 8 and divide it by this thing. Three exponent 8, 3 with 8 zeros, divided by, again, this is me, I like to put parentheses by my exponents. 8.85 exponent 13, close those parentheses. Getting 3.39 times 10 to the minus 6 meters. 3.39 times 10 to the minus 6 meters. So that's technically not our answer because they wanted in nanometers, right? So let's go ahead and quickly convert that to nanometers. So here's the conversion. 3.39 times 10 to the minus 6 meters times 1 meter. Okay, so 1 nano is small. Nano is like minus 9. So 1 meter. So 1 meter is going to have 10 to the 9 nanometers. Okay, there's a lot of nanometers because nano is small. Nano is small. A lot of nanos can fit into 1 meter. So 1 meter is 1 times 10 to the 9 nanometers. And what is that on our calculator? Times 1 exponent 9. What is that? 3,390 nanometers. So that will be our answer. So particles, and then we're getting wavelength, which is associated, with waves. All right, so that's that. All Right. These next couple of pages in our notes, if you're following along, kind of what I've summarized here, particularly the photoelectric effect. I'm just going to move on. Again, very, very quickly, okay, the idea of excitation and emission. Okay, and you can actually see here that the different emissions have different names associated with them. So if I were to just go to page 8, I know I'm hopping around, but these different emissions, the UV region of the electromagnetic spectrum, that's called the Lyman series. Visible for the hydrogen atom, that's called the Balmer series. That's when you're going from n equals 3 to n equals 1, n equals 4 energy level to n equals 2 energy level, n equals 5 energy level to n equals 2 energy level. These are all different emissions. Okay? All of these are different emissions as it relaxes back down. Okay, remember the key point here, as you relax back down, you emit. Not just invisible, as you can see here. You can emit in the UV region, you can emit in the infrared region, you can emit in all different regions of the electromagnetic spectrum. Here is our electron, that little red dot. This is exciting within the electron. Okay, I'm not talking about kicking out the electron. Okay, kicking out the electron, bam, just getting it out of the atom. Okay, that's something else. Okay, literally stripping the electron away from the atom, if with enough quanta so that it just gets liberated. That's not what I'm talking about. But giving it with enough energy so that it just is gone from the atom, that's called ionization energy. Okay, that's something we'll talk about a little bit later on. But ionization energy, where you literally kick out the electron from the atom, and you usually kick out, it's easier to kick out the outer electrons than the inner electrons in an atom. So that's IE, and it stands for ionization energy. This is not what I'm talking about. The photoelectric effect really is happening where there's energy levels inside the atom. Energy levels inside of the atom. And again, the electron can relax. As it relaxes, it emits. It emits all sorts of energy. Some of the energy we can see also. All right, so I just want to get that distinction for you guys. So I think for this interest of time, we'll just omit here, for those that are following in our notes, page 7 and page 8 and 9. So we will not talk about the de Broglie equation. So we will not talk about that, and we will not do the practice problem with it. So just in the interest of saving some time. Let's talk about now, shift gears and talk about quantum numbers. So, yeah, let's talk about quantum numbers here. All right, so let me introduce quantum numbers by giving you an. Let me give you the school's address. I won't give you my address. So the school's address is 5100 Ramsey Street, Fayetteville, North Carolina 28311. Okay. The old lectures I would actually give my address, but I don't think I'll do that. You're not shaking your head, yeah. That was smart. All right, so here's an address. Okay, just so happens to be the address of our school, right? And I want to ask you guys a question. So I want to ask you guys if you can give me 4 4 items that sort of summarize, just four items that summarize this address. Okay, you kind of know what I'm talking about. 4 things. 4 things that you think of, 4 items, 4 categories for this address. Zip code, very good. Okay, can you give me 3 more? Zip code, what else? Street, okay. Okay, 2 more. City, Fayetteville. And then 1 more. State, yep. Address, you can also, street name is that. Address, state, okay. So very good. So the idea is that if I give you these 4 things, is it not so? If I give you these 4 things, you should be able to find Methodist University, the location, right? These 4 items given to you will give you the location, right? Well, in the same way, we can determine the location, okay? I'm going to use it in air quotes. We can determine the location of electrons using 4 quantum numbers, okay? So, location of electrons are determined by 4 numbers, and those are called quantum numbers, all right? Sort of the address. Again, I'm using quotes. Why am I using quotes and why under location, and why am I using quotes under address? It's because of the Heisenberg uncertainty principle. See, we really can never know the true location. Okay, I reside in whatever, Falkland Court. Okay, that's my address. Okay, but you can't say so definitively for an electron. Number 1, because it's a wave and it's a particle. Number 2, it's all buzzing around, moving around the nucleus, right? So that's what the Heisenberg uncertainty principle entails. So you'll never know the momentum and the position of an electron. You just don't. There's always some uncertainty in determining a location of an electron. Having said that, our best guess are these 4 quantum numbers. Okay, just like the best guess of finding the school are these 4 numbers. Okay, the best guess for finding an electron, again, quote unquote, finding an electron, is these 4 quantum numbers. Realize Heisenberg uncertainty principle tells us we can never truly know for sure. We can never truly know for sure. Okay. All right, so what are these 4 quantum numbers? All right, these 4 quantum numbers for finding an electron. Okay, finding an electron. It's going to be N, L, M subscript L, M sub L, and then finally M sub S. Okay, so these are the 4 numbers that determine where, again, Heisenberg uncertainty principle, that determine where these electrons reside. Okay. All right, so this is a little bit complicated, but let me try to simplify it as best as I can. The 4th quantum number, let's do the easiest thing first. The 4th quantum number is called the spin. It's called the spin quantum number. Okay, and it's either spin up or spin down. Okay, so we can either take plus 1/2 or minus 1/2. That's it. It's either plus 1/2, minus 1/2. You see, the spin has to do with putting it in a big magnet. If you put it in a very large magnet, the electron will either orient with the magnet, we call that spin up, plus 1/2, or it will orient against the magnet, that's spin down, minus 1/2. Okay, so I usually tell people the 4th quantum number is very easy. Okay, it's either going to be plus 1/2 or minus 1/2. Plus 1/2 orienting with a magnetic field if you put it in a magnetic field, or minus 1/2 if you put it orients against a magnetic field if you put the element, the electron, in a magnetic field. All right, so either it's plus 1/2 or minus 1/2. Okay, N is the It's called the principal quantum number. Okay, you kind of saw n here, didn't we talk about n? I know I talked about n. N is called the principal quantum number. Okay, all the different energy levels. Okay, here's where I talked about n. Energy level 1, energy level 2, energy level 3. Okay, that's called the principal quantum number. And that's very easy also, because it's just the row in the periodic table. Okay, that is the row in the periodic table. I'll expand on that some more, but I assure you it's easy. Okay, it's the row in the periodic table where the element, whose electron you're trying to find. Row in the periodic table. Okay, row in the periodic table. So that's easy. The m sub s, the fourth quantum number, is easy, either 1/2 or -1/2. Okay, this L and m sub L is a little bit more complicated. So let's spend some time on that. Okay, you see, next page here. Okay, I'm on page 11. So here we go. N, L, m sub L, m sub S. Okay, so an electron's address, its house, okay? The electron's house is in an orbital. Okay, so electrons reside in orbitals, okay? These orbitals have shapes and geometries. You actually see some of the orbitals here. Okay? So these are not all the orbitals, but so here's one orbital. So an electron, again, wave particle, its electron density resembles a sphere. Okay, that's one shape. These are all weird. Okay, here the electron density represents, I don't know, whatever you call this shape. This one is a dumbbell. So again, the probability of finding an electron is a dumbbell. Okay. Here's the dumbbell. Here the probability of finding an electron is a dumbbell. So the probability of finding an electron is high here, 0 right at the center. That's called a node, where there's no energy. So all of these different shapes and sizes of trying to find an electron. You gotta remember, electron is wave, it's particle, and there's an uncertainty. So these are like, it's like statistical mechanics, a very, very high level of math. Trying to find statistical probability of finding an electron, which again is a cloud, which again is a wave, which again is a particle. So it gets complicated. Anyways, these electrons are going to reside in orbitals. Let me give you the orbitals now. Okay, it can reside in what's called an s orbital. Okay, there's only one slot in an s orbital. Okay. It could reside in a p orbital. There's 3 slots. Maybe kitchen, bathroom, closet. Okay, p orbital. Okay, there's 3 slots. And then in the d orbital, there's 5 slots. And then there's an f orbital. We will not talk about it, but I'll just tell you, in an f orbital, the electrons have 7 slots. 1, 2, 3, 4, 5, 6, 7. I actually have the shape of these on the next page in our notes. So again, the electrons are going to reside in orbitals. Okay, they're going to reside in orbitals. The s orbital looks like a sphere. Okay, the s orbital looks like a sphere. Let me just jump really quickly to another page here. The s orbital looks like this. Okay, the probability of finding an electron in the s orbital resembles a sphere of electron density. Okay, so that is what an s orbital is. For now, that is where an electron can reside. The p orbital resembles a dumbbell. Okay, this is the shape of a p orbital. All right, dumbbell along the x, dumbbell along the y, dumbbell along the z, dumbbell along the x, dumbbell along the y, dumbbell along the z. Okay, the d orbital is really complicated. It has all these different shapes for the 5 slots. Again, we're talking about where an electron can reside. I don't even know the names of these shapes, okay, but it's complicated geometry, okay. So here are the 5 slots where an electron can go for the d orbital and their shapes. Remember, the s orbital has 1 slot, and then the p orbital has 3 slots, okay. Dumbbell shape along the x, y, a dumbbell shape along the y, and then a dumbbell shape along the z. So this L principal quantum number tells you the identity of the orbital. Okay, the identity of the orbital. Okay, you have to memorize this code. Okay. This L, the second quantum number, is the identity of the orbital. So if your L is 0, okay, you are talking about I have the code right here, but if your L is 0, you're talking about an s orbital. This is just something you'll have to memorize. You'll have to bite the bullets. Okay, we're talking about the second number in our address. If your L is 1, we're talking about a p orbital. Okay, if your L is 2, we're talking about a d orbital. I'm not going to ask you this on any exam, but if your L is 3, which I'm not going to go over, this is an f orbital. Okay, I cannot imagine what f orbitals look like, but I'm sure you can find it on the internet. It's complicated shape. All right, so just memorize this code for our second number. Okay, I'll put an orange box here. All right, so L gives the type of orbital type. Okay, m sub L is what's called the orientation quantum number. Okay, the second and the third are a little bit complicated, but this is called the orientation quantum number. You see, within the orbital, where is it residing? Within the orbital, we already defined the orbital now, okay, S, P, D, or F. Where within the orbital is it residing? The kitchen, the bathroom, the living room, whatever, okay? If the house is the S, if the house is the P, if the house is in the D orbital. All right, here's how you're going to do this. All right, so I'm talking about m sub L here. All right, 1 slot, m sub, for the s orbital, there's only 1 slot. The m sub L is going to be 0. The third quantum number will be 0. Okay, that's it. Okay, period, paragraph. The m sub L for the p orbital, okay, here's how you're going to do that. Okay, you're going to take that center slot. That center slot will always be 0. The center slot will always be 0. And then you're going to go sequentially. So here it's going to be +1, and then the other side it's going to be -1. Okay, I'm talking about m sub L. So m sub L for a p orbital, it could either be in the -1 slot. It could be where the electrons go. It could be in the 0 slot, or it could be in the +1 slot. Okay, this is a little confusing, but I'm talking about the third number in our address. Okay, m sub L for a d orbital. You're going to take that center slot, and that becomes 0. Okay, the center slot becomes 0. And then you're going to go sequentially, okay, +1, +2 on the right, and then on the left it's going to be -2, -1. So here the electrons can go in -2, they can go in -1, they can go in 0, they can go in +1, or they can go in the +2 slot. Think of it as different rooms in a house. The house here is the d orbital. Okay, the third quantum number, m sub L. Okay, finally, I'm not going to talk about F, but just for completeness, m sub L for F, the center one is 0, then we're just going to go to the left and to the right sequentially. So for the F orbital, m sub L can go in the -3, it can go -2, -1, 0, +1, +2, or +3. Okay, so that's our third quantum number. All right, so here's how the electrons are going to go. Okay, the electrons in the s orbital are going to pair up, spin up, spin up, or spin down. So they pair. Okay, the order the electrons go marching in. The electrons go marching in. Hurrah, hurrah! They're going to march in. Okay, so the s orbital, spin up, spin down. And the p orbital, they're going to march, spin up, spin up, spin up, +1/2, +1/2, +1/2. Then what? They will go spin down and pair. Okay, -1/2 spin down, -1/2 spin down, -1/2 spin down. Okay, let's go to the d orbitals. How will they go in d? The electrons go marching in, hurrah, hurrah. Okay, spin up, spin up, spin up, spin up, spin up, +1/2, +1/2, +1/2, +1/2, +1/2. Now what? They're going to pair. They're going to pair spin down, -1/2, spin down, -1/2, spin down, -1/2, spin down, -1/2, spin down, -1/2. That's how the electrons go marching in. Hurrah, hurrah. Okay? That's how the electrons go marching in. In the s orbital, they'll pair because the s orbital is very low energy, very close to the nucleus. Once they go to the p, spin up, spin up, spin up, then down, down, down. Once they go to the d, spin up, spin up, spin up, then spin down, spin down, spin down. Right? Okay, don't forget m sub s. It's either going to be +1/2 or -1/2. Right? So that is the 4 quantum numbers. It's kind of tricky, but we can do some examples to bring some clarity to this situation. All right. By the way, these are how the orbitals look like. Just want to tell you they have a very specific shape, very specific geometry, very specific orientation. Okay, and look at all the different geometries. Okay. This is the s orbital. It's shaped like a sphere. Okay, don't forget L is equal to 0. And what does this 1, 2, and 3 mean? The 1, 2, and 3 is n, the principal quantum number. What about a p orbital? What's the principal quantum number for a p orbital? Okay, here it's going to be 2. You see that? N equals 2. Okay, what is L for a p orbital? L equals 1 for a p orbital. Okay, how do I know that? That's just something you're going to have to memorize. Okay, that's just something you're going to have to memorize. L equals 1 is code for a p orbital. Now within that p orbital, it can go in the 0 slot, the -1 slot, or the +1 slot. That's m sub L. Right? And then within that, it goes spin up, spin up, spin up, spin down, spin down, spin down. How about this? Well, actually, let's do an example. Let's do an example. All right, so write the four quantum numbers for an electron in a 3p orbital. Okay? So n, l, m sub l, and then m sub s. So this will be something that you'll see on the exam. Okay? And it's very simple. Okay? It's very simple. All right, first of all, what is a 3p orbital? How many slots are in p? How many slots are in p? There's 3 slots in p. Okay? Okay, not just p, we're talking about 3p. Okay, 3p. Okay, there's 3 slots in p. Again, remember the shape, how these look like. Dumbbell for the p orbital, dumbbell along x, dumbbell along y, and then a dumbbell along z axis. So n, l, m sub l, m sub s. Okay, so first of all, what is n here? N is going to be 3. Okay. How will the electrons go? Okay. This is how they go for p. Spin up, spin up, spin up. And instead of going to a next higher level orbital, they're going to go spin down. They'll pair up, spin down, and spin down. Spin up, spin up, spin up, spin down, spin down, spin down. All right, what is L for a p orbital? What's L for a p orbital? 1. 1. Okay, so 3, 1. Okay, let's look at this electron here. 3, 1. All right. And what is m sub l? Remember, the center slot gets 0. And then we go +1 to the right, and then -1 to the left. All right. So what is m sub l for this electron with the red dot? -1. And is it spin up or spin down? This electron. Pointing up or down? Yeah, if it's pointing up, we'll just call it +1/2 spin up. Okay. Okay, so that's the quote-unquote address for this electron. Okay, how about this second electron here? Okay, what's the principal quantum number? Still going to be 3. Okay, what is L for a p orbital? What's L for a p orbital? 1. Very good. Okay, where's this electron located? What m sub l is it? -1. And then spin up or spin down? Spin down, it's going to be -1/2. So that's the address for this purple electron.
So you have to do it. So we're going to have like 6 different answers?
Yeah, you'll have 6 answers, each with 4 numbers. Because remember, the p orbital holds 6 electrons.
Okay.
Yep, very good. Oopsie, sorry. Okay, we got 4 more to go. Let's do the orange one here, orange asterisk. Okay, what will the orange asterisk be? 3. L is 1 for a p orbital. What is the m sub l here? 0. Is it spin 1/2 or spin? It's +1/2 spin up. Okay. Okay, let's do the square electron. The square electron here is everything is the same except it's spin down. Everyone see that? Okay, everything is the same except it's spin down. Remember, all of these addresses have to be unique. Okay, this is different than this because one is spin up, the other is spin down. All right, 2 more to go. How about this black dot electron right here? Okay, what do you guys think that will be? 3, 1. Everyone see +1, and it's +1/2. Okay, everyone see that? And then finally this circle electron. Everything's the same, 3, 1, 1 -1/2. And that is the answer to this question. Okay, all the electron addresses of when they fill a 3p orbital.
Do you have to write it in the parentheses like that? Or can I write N equals L equals?
I would prefer the parentheses. I think that's how the textbook does it. So that's just their convention. I mean, you're also right, but I think they want it this way. That's a good question. Right, so yeah. Okay, how about 4D? Okay, remember, how many slots does the D hold? Okay, 5. Remember, 5. 1, 2, 3, 4, 5. It's 4D. Okay, how will the electrons go in D? Okay, spin up, spin up, spin up, spin up, spin up. And then what? Are they going to go to the next level, or are they going to they'll pair up? Okay, it's better to pair up than go higher energy. Okay, spin down, spin down, spin down, spin down, spin down. All right. Always take that center orbital, that center. What is that called? Shell, slot, whatever you call it. Okay, the center one becomes 0. And then we're going to just number them +1, +2, and then this is -2, -1. Sort of the individual slots here. That will be your M sub L. All right, so let's just do this here. I'm going to number them 1, 2, 3, 4, 5, electron 6, 7, 8. I'm just going to number them just for ease. Okay. So what will be 1? Okay. Principal quantum number n is, everyone see it's 4? Everyone getting that? It's 4. 4. What is L for a d orbital? This is something you'll have to memorize. What is L for the d orbital? Okay, everyone see 2? Okay. So 4, 2. Okay, what position is this electron in? Everyone see -2. And is it spin up or spin down? Spin up. Okay, so that is electron, location of this electron. Just forget that. Okay, and then are we good at finishing up the other 9? 4, 2, -2, -1/2, right? Someone stop me if you're having issues. 4, 2, -1 +1/2. Yes? 4, 2, -1 -1/2. Okay, are we okay with this? Someone stop me if you're having issues. 4, 2, 0 +1/2. Okay, 4, 2, 0 -1/2. I don't know where you guys are, but I'm moving along. Hopefully you're getting it. Okay, 4, 2. What's next here? +1 +1/2. Okay. 4, 2 +1 -1/2. Spin down. Okay, my last slot. Are we all good? 1, 2, 3, 4, 5, 6, 7, Yeah. 4, 2, 2. Right? This is 4, 2, 2. Spin up plus 1/2. And then finally 4, 2, 2. Minus 1/2. So 4D is going to be, those are the addresses for all of those 10 electrons. Addresses I'm going to use in quotes. Okay, so these are the 4 quantum numbers. Okay, so this electron here in the red circle is defined by this location. 4, 2, minus 2, plus 1/2. Okay. That's quantum numbers. All right. Let me do one more. Okay. How about the 2s orbital? Okay. Write down all the quantum numbers for the 2s orbital. Okay, so how many slots are in s? It's just one slot. Okay, it's just one slot, 2s. Right, what is the principal quantum number? Okay, the principal quantum number is the number in front of the orbital, so that's 2. Okay, what is L for an s orbital? Again, you just have to memorize this. What's L for an s orbital? 0. Okay, what's m sub L? It's also 0. There's no other slot. There's only one slot. Okay, so that's also 0. And then how does it go? Plus 1/2, minus 1/2. So that would be the answer for a 2s orbital. Okay, so here's the address for this guy. Here's the address for that electron. All right. So something like this on the exam, all right? Multiple choice or whatever problem set, or your quiz number 4, okay? So make sure you're comfortable doing this. The key here is, knowing what L and m sub L are. Okay, here's L, and then here's m sub L. In the last 10 or so minutes, let's go over electron configuration. Oops. Right, so the electrons go marching in. Okay, hurrah, hurrah. That's how the electrons are going to go marching in. Okay, that's literally what electron configuration is. They go marching in, hurrah, hurrah. So how will they march in? Okay, electrons are going to march in a very specific order. And I think that order is something I have here. Here. Oh, I'm dropping everything. Time for me to go. All right. They're going to go in a very specific order. Okay, so so here are the order. Okay, so we have, first of all, let me just tell you, this is n equals 1. That's principal quantum number 1. The second row is n equals 2. The third row is n equals 3. The fourth row is n equals 4. But I want to bring your attention to right here. Okay, what's in this box here? So this is where things get confusing. Okay, what's in this box here? Okay, the transition metals is the n-1 block. Okay, so the electrons are going to go. They're going to march, march, march. After they march to 4s1 and 4s2, they will go to 3d. Okay, after they march from 4s1, 4s2, they're going to go to 3d. And then from 3d, they go back to 4p. Okay, 4p. Okay, I'm going to talk more about this later. So, all right. So that's n equals 4, n equals 5. something happens at n equals 6. Okay, so after the electrons fill up 5p, they go to 5s. Okay, after 5s, they go to 4d, so 5s2, 4d. Remember, the transition metals are n minus 1. After 4d, the electrons are going to march to fill up 5p. Okay, after they fill up 5p, they're going to march to go to 6s. After 6s, they're going to go to the n minus 2 block. The n minus 2 block is right here. They're going to go to the n minus 2 block. So after 6s, they go to n minus 2, the f block. The f block is right here at the bottom of your periodic table. Okay, they're going to fill up the f electrons. And then they're going to go all the way back to fill up the d electrons. Remember, electron, I want you to recognize, if you don't get the nitty-gritty, the electrons are going in a specific order. That's all I'm trying to tell you here. So after 6s, they're going to fill up 4f, then go back, fill up 5d, fill up 6p. Okay, then go to 7s. After 7s, what happens? Okay, they're going to fill up 5f. After 5f, okay, they're going to fill up 6d, and then finally 7p. Okay, so the order, how the electrons go marching in. The electrons go marching in, hurrah, hurrah. This is how they're going to march in. Okay, something weird happens after 6s. After 6s, they go to the n minus 2. Okay, so 6 minus 2 is 4, so after 6s, they go to 4f. 4f, they go to 5d. Okay, so let's think about this a little bit more specifically now. Okay. So I would use this as a guide to tell you the order in which they go. Okay. All right, notice here what's on the y-axis, energy. Okay, energy. So we are going higher and higher and higher energy levels. Okay, kind of like going to a football game. Okay, I don't know if you like this analogy or not. Going to a football game, closer seats, the electrons are going to go, and then they march in farther, 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 farther away. Okay, higher, 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 higher energy, farther, farther, farther away from the nucleus. Okay, so let's do this thing here. All right, the first element in the periodic table is hydrogen. So, yeah, hydrogen is 1s1. How many electrons are in hydrogen? 1, right? You agree? How many electrons are in hydrogen? 1. So the electron configuration of hydrogen is 1s1. All right, what's the hydrogen? All right, next element on our list is helium. How many electrons in helium? 2. Where will that electron go? Is it going to go to 2s or will it pair up? You know, why go all the way in higher energy? Okay, we'll just pair up. So helium, next on our list, is going to be 1s2. Okay, what's special about helium? Completely filled 1s orbital. Completely filled 1s orbital. That's why helium is a noble gas. Okay, the n equals 1 shell is completely full. The n equals 1 shell is completely full. You're going to see that for all the noble gases. All right, next element, 3. How many electrons in lithium? By itself, lithium is 3 electrons. So 1, 2, 3. So lithium is 1s2, 2s1. By the way, what is 1s2? What is 1s2? What? 1s2 is helium, right? So the electron configuration for lithium is helium 2s1, I'm sorry. All right, what's next on here? Beryllium. All right, where will that electron go to beryllium? Is it going to go to 3s or will it pair up? It's going to pair up. So for beryllium, which is the next element on this list, it's going to be helium 2s2. Everyone see that? Helium 2s2. 1s2, 2s2, which is the same thing as helium 2s2. All right, from beryllium, we hop on over to, what happens? We're going to hop on over to boron. Okay, boron. So where will that electron go for boron? Again, the order. Okay, after 1s, it goes to 2s. After 2s, where will it go? After 2s, where does it go? 2p. Okay, after 2s, the fifth electron in boron is going to fill the 2p shell. So it's going to go right here. 5 electrons. 5 electrons in boron. 1, 2, 3, 4, 5. So boron is going to be helium 2s2, 2p1. What's carbon going to be? Helium is its nearest noble gas. Okay, we got to fill 6 electrons, so we're going to fill 2 of them from helium. 2s2, 2p1, 2p2. Okay, and that electron is going to go this way. Okay, spin up and then spin up. Okay, that's the order in which they go. Okay, so carbon is going to be helium 2s2, 2p2. All right, nitrogen. What would nitrogen be? Nitrogen is next on the list. 7 electrons, 2 of them from helium. 2s2, 2p1, 2p2, 2p3. Okay, it's going to go spin up, spin up, spin up. Okay, so nitrogen is helium 2s2, 2p3. Oxygen is next, 8 electrons. 2 from helium, 2s2, 2p1, 2p2, 2p3, 2p4. Okay, now we're going to go spin down, right? It's going to pair up. Instead of going to a higher energy level, it's going to pair up. So oxygen, the next element in the periodic table, is going to be helium 2s2, 2p4. Okay, after oxygen is fluorine. Fluorine has 9 electrons. Okay, how will the electrons go? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9. They're going to pair up right there. So fluorine is going to be helium 2s2, 2p5, and then finally the noble gas neon, 10 electrons, a completely filled 2 orbital, n equals 2 orbitals. So neon is going to be helium 2s2, 2p5, and then 2p6, I'm sorry, helium 2s2, 2p6. Yeah. noble gas. Helium 2s2 2p6. Actually, neon is just neon because it completely filled n equals 2, right? This whole thing is filled up, the electron configuration for neon. All right, let's do 3s, 3p. Let's do some of the 3ds here. Sodium. Okay, sodium has 11 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So sodium is going to be neon, the 10 electrons, and now it's 3s1. All right, next one after sodium is magnesium, Mg. So magnesium, we're going to fill up that 3s. So magnesium is helium 3s2. Yep.
Why are you still using like helium? I thought.
Yes. Yep. Thank you. Appreciate it. Yes, neon 3s2. Thank you, Harris. Yep. She got me. That's good. Just paying attention. Yeah. Right? Nearest noble gas for sodium is neon. All right. Aluminum after 3s. Okay, the electrons go marching in. Hurrah, hurrah. They're going to go in a very specific order. After 3s, where are they going to go? 3p. Okay, so aluminum is 13 electrons. So we already got 12. It's going to fill 3p. So aluminum is neon 3s2 3p1. Let's move on kind of quickly here. Silicon, 14 electrons. Okay, we go up, spin up. So silicon is going to be neon 3s2 3p2. Phosphorus, 15 electrons. Okay, they're going to spin up. Remember, spin up, spin up, spin up. Phosphorus is going to be neon 3s2 3p3. All right. Sulfur will be neon 3s2 3p4. Okay, everyone see that? Chlorine. Argon will have a completely filled 3 shell. Argon will have a completely filled 3 shell. So okay, so we're going to doom 4s. Okay, this is where I want to get to you guys. I filled up the 4s. Okay, so after 4s, so potassium. Let's go to potassium here. Potassium is going to be argon 4s1. Does everyone agree? Okay. Yes. Okay. All right. Calcium. Calcium is going to be argon 4s2. All right, this is where I want to get you guys because it can be confusing. Okay, what's scandium? Scandium is argon. Okay, scandium Sc has 21 electrons. Scandium has 21 electrons. We're going to fill out 18 like it's from argon. The 18 come from argon. And then we have 4s2. The electrons will go to 4s2. All right, 3d1. Okay, that's the key point, 3d1. So after 4s, where do you go? You don't go to 4p. After 4s, where do you go? 3D. And then after 3D, where do you go? 4P. Okay. After 4P, where do you go? 5S. After 5S, where do you go? 4D. After 4D, where do you go? 5P. After 5P, where do you go? 6S. Careful. After 6S, where do you go? 4F. Very good. After 4F, where do you go now? 5D. The electrons go marching in, hurrah, hurrah, in an order. After 5D, where do you go? 6P. After 6P, where do you go? 7S. After 7S, where do you go? Be careful. 5F. After 5F, where do you go? Thank you. 6D. And after 6D, where do you go? 7P. Okay, so the order of how they march in is basically electron configuration. That's actually shown here. Okay. You want to look at this. Okay, first 1S, then 2S, 1S, then 2S, then 2P, 3S, 3P, 4S. After 4S, 3D. After 5S, 4D. After 6S, 4F. Okay. After 7S, 5F, then 6D, then 7P. So yes, electrons go marching in, but you have to know the order in which they march in. Once you know the order in which they march in, I want to hopefully convince you that this electron configuration business isn't so bad. All right, thank you so much for attending. And I think I took you a little bit over time. Let's finish this up next week. And, labs are available. We're looking for people to come and do labs. Okay? If you want to come Wednesday or Thursday, it's fine.
If it's on Wednesday, is it the same time?
Yes, the same time.
Okay.
So lab reports, last 2 lab reports, and then 8, I'm going to go kind of fast, and 9 and 10 is the big one, and that will end the course with 9 and 10. I'm combining 9 and 10 together. Thank you guys. Did you guys get this? Got it? Did you get this, Harris?
Thank you.
Thank you. Bye, guys.